notes today. Types of bonds. This is only going to be a discussion of intramolecular bonds, meaning within the molecule, this atom is attached to that atom, and it makes a molecule, not how it's attached to the next molecule. That's the next unit. All right. We'll hit solids and liquids in the next unit. So we have to talk about the three different types of bonds, whether electrons are shared equally, unequally, or just outright stolen from one to the other. And this really comes down to the strength of the atoms, and we're going to hit that again and again and again. If they're shared equally, we call it covalent. Unequally shared, polar covalent. And if it's completely unequal, it's ionic. And then you actually have a full-on positive and negative charge. So ionic bonding, after the electrons are exchanged from metal to non-metal, the ionic bonding is actually held together through something called electrostatic attraction. And electrostatic attraction can be described using this here. What does that look a whole lot like? If it was an F instead of an E, it would look like Coulomb's law. It pretty much is Coulomb's law. It's slightly different. We don't, again, just like with Coulomb's law, we're not doing any math with this. It is just an equation to explain some of the things that are going on. The E is an energy relationship, though. As ions come closer together or farther apart, the amount of energy released or absorbed changes. R is the distance between the ion centers in nanometers. Again, we don't do the math. It's the distance between one ion and the other ion, but the center of the ion, which we usually call the nucleus, right? I'm going to put the emphasis in a weird spot, the nucleus, right? Yeah, so it's the distance between my nucleus and your nucleus, and that's, for some reason, an R here. You could go real deep. I could see the birthday boy over here going like, hey, why isn't it R squared? It really doesn't matter to us because we're not doing the math. Whereas Coulomb's law is R squared. And there's this really fancy explanation out there on the internets about that. But what are the Q values? The Q values might be our positive value. Let's see down here. We have magnesium as a +2 and oxygen is a -2. So those are the two Q values, the +2 for the magnesium, the -2 for the oxygen. That should be a plus sign. It looks like a new symbol. And so the energy is going to be proportional not just to the distance, but to the value of the charge. Would the energy relationship be more or less if the positive charge was, say, +1? It'd be less. It'd be half as much, right? And that's going to come into play a little bit later. We'll come back to why that's important in a minute. But we don't actually do these calculations. We just think about how the values would change if I doubled the charge, or if I reduced the charge relative. So if I was a +3 and you're a +1, and we're both attracted to a -2, which attraction would be stronger? Right? The +3 and to the -2 would be stronger. Covalent bonding. In covalent bonding, we're talking about electrons being shared. Again, this is actually an energy scenario. The protons in my nucleus are attracted to all electrons, whether or not they belong to me or to you. And so I pull on your electrons, and you are protons that are pulling on my electrons, and we're all pulling on each other, and we end up kind of, again, kind of like that equation we just saw. They get pulled towards each other, and there's a certain distance that's the awesome distance, where both nuclei are sharing electrons in common. There is a particular distance. Do you think that distance is consistent from one atom to the next atom, or do you think it varies from one atom to the next atom? It's going to vary. It's going to vary on a couple things. How many protons does nitrogen have versus how many protons does fluorine have? It's also going to vary dependent upon, so wait, let me write that down. If I'm talking about the number of protons, I'm probably talking about our friend CF, effective nuclear charge, right? The other thing that might come into play is how many, guess what? How much shielding effect due to energy levels. If you were to compare oxygen to tellurium, tellurium has way more energy levels, right? So its nucleus is by definition going to be farther from its valence electrons and even further away from, say, your valence electrons, as the nucleus of tellurium tries to bond to the valence electrons in another atom. They're really far away. There's a lot of electrons shielding their attachment, so you're going to see different sizes in molecules. A larger molecule is probably not as strong a molecule, probably breaks easier. Those are other things we'll talk about today. Shielding, running out of room, effect. Just going to write right over top of those. We are later going to review how to draw Lewis dot structures, okay? How to draw those bonds and molecules and everything. I have some amazing drawings coming up. That was sarcasm. Here's a old school drawing that's not in your notes, but this is the old kind of Bohr model of the atom as electrons are in energy levels and they're being shared. We don't usually ever draw this. We draw the Lewis dot structures. But I do like to occasionally color code my drawings later. So you can see on the first one, they use red and blue to represent the different atoms to make it easier to see. You guys could do that in homework. It makes it a lot easier when you're drawing, if you're drawing multiple colors. It really does. I tend to draw in 3 different colors if it's an ion. I tend to draw in one color for one atom, so maybe all the oxygen atoms, I make the dots red. And if there's a fluorine in a phosphorus in the middle, maybe I make the electrons for the phosphorus blue. And maybe there's a -3 charge, which means I get to add 3 electrons. I might make those green, just so that I know that I didn't add too many electrons and I can easily keep track of them. Then we have polar covalent bonds. Polar covalent is the category where they're sharing, but they're not equally sharing. And this is really going to come down to who's stronger or who's weaker. What do you suppose determines whether or not an element is stronger than another element when they start to pull at each other's electrons? The number of protons, right? The number of protons or effective nuclear charge. And the other thing also? Shielding effect. So there's 2 things that are going to be kind of juxtaposed against each other. But they both get represented in this term called electronegativity, which is what we're hopping into next, is what the heck is electronegativity. That is a term we used in chemistry last year, right? Dark side initiates, you remember that? Yes? Okay. So electronegativity is the ability of an atom or in a molecule to attract the shared electrons to itself. So you have 2 elements, let's say fluorine and oxygen, and fluorine has 7 valence electrons. Oxygen has 6 valence electrons. And they're going to share some of these electrons in common. I'm just doing a real crude drawing. Let's say they're sharing those 2 that I just put in the lasso. They're sharing those electrons in common. Which element do you suppose is stronger, fluorine or oxygen? Let's try to go through the reasoning behind this. Fluorine. Do they have the same shielding effect, fluorine and oxygen? They do have the same shielding effect because they're on the same period, the same energy level. However, which has more protons? So it has a higher effective nuclear charge because fluorine has more protons. So these 2 shared electrons, and this is would be shifted, and so fluorine would be slightly negative, and the oxygen would be slightly positive with respect to that bond. All right, that bond, the electrons wouldn't be 50-50 shared; it might be 60-40. All right, it depends on who's the stronger element. What is that symbol? That symbol is a lowercase delta. I can't go back a page. I mean, it's one thing I don't like about this recording is I can't go back. That's my attempt at a nicer version of it. It kind of looks like a funky, fancy letter D. You know what the uppercase delta looks like, right? It's triangle, which is a letter D that kind of got squished a little bit, right? Because the Greek letters are precursors to our letters. So they've slowly evolved, and languages do evolve, and the symbols. I mean, look at my handwriting. I think we're devolving. So Now, you don't usually see people requesting you mark which side's negative or which side's positive, but looking at a molecule and saying, yes, there would be polarity in a bond, or no, there would not be polarity in a bond. It really comes down to the electronegativity trends. And we have a graph here. Can you see the special trend again? This is almost the same graph we had last unit. Guess which elements these are in the red blob I just circled. It's the two S's and the two P's. And as you go across, it's 2S, 2S2, 2P1, 2P2, and all the way to fluorine. And then there's a drop to 0. At what element? Neon. And electronegativity is the pull of on electrons in a shared bond. Why is neon's value 0? It's a noble gas. It doesn't form bonds. It's already got a full and stable energy level, or shell, if you will. And then look at how the values in the next thing seem to have all dropped a smidge, don't they? They're all a little bit lower. What is going on in the third energy level? Shielding, which is why we see the slow drop. And you see it again kind of in the next one. It gets a little funky. Why is it getting funky here? Those are your d orbitals messing everything up. Those dumb d orbitals. I think that's, yeah. Nope, that didn't work. Okay. So as we look across this little periodic table, we see there aren't any noble gases on there. The noble gases are missing because their value would be 0. The strongest element on the list is fluorine. Where do we suppose we spend most of our time? Yeah, we spend a lot of our time in this little corner over here. There's one element not in that corner that we do use a lot, and that is hydrogen. I want you to find a new home for hydrogen in the place I circled the first time. What element is just as strong as hydrogen in that little circle over there? Phosphorus. So a lot of people remember pH go together. That shouldn't be too funny. No, that's not how you spell funny. But if you remember that phosphorus and hydrogen are the same strength, you can go, okay, if I have hydrogen and sulfur, which element should be stronger? Or sulfur or phosphorus? So you see what I just did there? I switched hydrogen in my head to phosphorus for the comparison, and then I could go back to using the right word on paper. But I just automatically switch hydrogen and phosphorus when I'm talking about who is stronger, who has higher electronegativity.
You're saying they have the same electronegativity.
They have the same electronegativity. So what would a hydrogen-phosphorus bond be covalent or polar covalent? Just be straight up covalent because they're equal strength. This is actually just a weird kind of like, we have more protons, so I have a higher effective nuclear charge, making it stronger, 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 but we have more shielding, making it weaker, and they've just kind of canceled each other out when you got from hydrogen to phosphorus. Benny Ben. I don't know the unit. Let's call it Bs, all right? It's 4.0 Bs. Now, I don't know. It's probably got a unit. It's probably in kilojoules per blah, 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 blah. But we don't usually do too much math with electronegativity. We just kind of think about relative position. If you have elements in this corner fighting against each other, the closer they are to fluorine, the stronger they are. And like in previous units, we typically only compare within a group or within a period or within a group. We don't usually go diagonal, 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 diagonal and make it evil because it's too hard to do the prediction because you're not going to be given the data table. But you are maybe asked to say, would the carbon-fluorine bond be polar? Yes. Not how polar, all right? Now what happens if you have anybody in the, I'm now going to make it orange, in the orange circle versus somebody over here? Would it be polar? It'd be ionic. It would probably be ionic because you have the really strong elements against the really weak elements, and the electrons don't get shared. Initially, they get shared. They come up to each other, and there's a temporary sharing, and they're like, nope, that's my cookie. And they just take it, and they walk away. I told you we were going to share, but then I realized I wanted it more. So, and the fluorine strips them off. Yes?
So these electronegativity numbers are calculated from that first equation that looks like coulombs.
A little bit, yeah. It's a slightly more complicated equation than that.
And that's just like based off the protons and shielding and that.
Yep, yep. And then also backed up by observation. You know, there you can build these things in a lab and measure how strong things are, how much energy you have to put in to break it apart. I imagine that's a fun job. Let's just break molecules and see what happens. Crank up the gamma radiation. So I think we just hit all of this stuff about electronegativity, the ability of an atom to attract electrons to itself. The greater difference, the closer it's going to be to ionic. If they're really far apart, it's definitely ionic.
Like regions, like I think we learned it last year. It's like from this much to this much, it's going to be ionic.
So there are values that are cut off, so we're going to get into that in a little bit. But the only time something is truly covalent is if they are actually equal in strength. Then there's polar covalent, any slight difference at all. And then there's ionic, because you have a huge difference. Yes, there are mathematical values. You can usually predict just based off of the position on the periodic table. They're kind of close together, polar, pretty far apart, ionic. It does get pretty evil with alloys, but we don't typically really get into alloys. We gotta go general on alloys, not too specific, because that's an entire class all by itself to really understand how alloys work. And we've already explained the trend in terms of effective nuclear charge and shielding effect a whole lot, haven't we? All right, we're moving on. And then here we have just some examples where people are comparing the two differences and talking about the fact that they have, that's a different term. So we're going to hit this term again later, but that's actually a term that doesn't refer to the bond. So a bond is between two atoms, and then after all of the bonds are formed, you have a molecule, don't you? Well, what if we have, these are all too simple, and that's why it's being used here. What if I had an atom, and it was bonded to two fluorines, and in both cases, the fluorine was stronger and the fluorine was stronger. Like it's getting pulled, that X atom is being pulled towards the fluorine and the other fluorine, okay? So the term dipole moment applies to all of those bonds at once. So if you averaged them all together. So if you averaged that orange one to the down left and to the down right, what's an average of down left and down right? Down center, right? You see, like you add the vectors together. We don't really do that, but you can when you get into another level of chemistry. Yeah, a little bit of physics, a little bit of chemistry. It crosses the line, kind of gets blurry. The reason they're using it here is these are homonuclear molecules. What the heck was that phrase? It's just one atom to one atom. So if the bond is polar, it also has a dipole moment that matches it. But if there's multiple bonds, then you kind of have to average them out. The best way to figure that out when you're starting is to build models. Like to draw the Lewis dot structure and then build the model and go, wait, this isn't flat. This is 3D. How about we do that on Friday when people are already going to be kind of distracted because of the homecoming and the pep rally is going to occur like right before this class and all that stuff. So when we come back from the pep rally, you guys will build models, draw Lewis dot structures, and just kind of have a, and that's also going to be our lab. People are going to struggle. People wearing Def Leppard shirts aren't good at making dots. They just struggle with that. And so they might need help. But you guys kind of work together. I'm going to be out next class. You guys are going to work together. I'm going to guarantee the sub won't have a clue what you guys are talking about. You're going to work your way through some hard problems. When I come back the next day, we'll like tackle the hard ones. Okay? It'll be a mix of hard and easy. But Yeah, you're just going to do a lab report talking about how you figured out if this was tetrahedral or bent and stuff like that. And not much of a procedure other than draw Lewis dot structures, build the model, compare the model to the paper, and you kind of see on paper it looks two-dimensional or it looks linear. But once I build the model, I can see, oh, it's actually bent, you know, and you really start to get rid of some of the misconceptions we have. Because the world is not flat. It's three-dimensional. Oops. All right. Based on their atoms, which one do you think is the most electronegative of those five? Which is the most electronegative? Oxygen. Oxygen. Okay, so I'm going to write most on that one. Which one do you think is the least electronegative of those five? Just barely cesium. Right. Barium would probably be right after that. And then strontium, and then selenium is the second most. And then this one here, number 4, calculate the difference in electric. No, I'm not going to calculate the difference. I want you to estimate the difference. I want you to think about their position on the periodic table. Which of those would probably be the most ionic, don't you think? The most ionic. Rubidium and oxygen are literally the farthest two apart, aren't they? That one's probably the most ionic. I'm going to write ionic really big. All right. And then nickel. Nickel's probably also ionic, but not as ionic because they're not quite as far apart. Lithium hydride? Where's lithium and hydrogen? No. No, they're not. No, they're not. No, they're not. Where's hydrogen? It's over there in phosphorus. That's why the trick question's in there. So we smash that mistake right now with a tiny hammer. It's not a big hammer. Tink, tink, tink. Yeah, so they are really far apart. So this one's probably ionic also. It is getting difficult to predict. All right. Hydrogen and fluorine technically are right on the edge of polar and ionic. They're like if the cutoff is like 2.5, and I think they are 2.5. And so you're like, what do I do? Well, the answer is, this is gray. This is not black and white. All right, there's a lot of shades of gray as you're going about what is ionic, what is this. And in just a second, we're going to, and a little bit later, we're going to talk about how nothing is truly covalent unless it's oxygen and oxygen. Unless it's your identical twin you're having a tug of war with. It's always going to have a little bit of partial ionic to it. You already saw my amazing delta symbols, right? That's the same thing. That's not my hand drawn. That's actually typed. Why is the hydrogen got the slightly positive or delta positive value? Well, you can use the term electronegativity here. Which one is more electronegative? Fluorine. So fluorine would be drawing the electrons to it more than the hydrogen would. And then as far as a dipole moment, we would say, what's the proper way to do this, even though we never do it? So this arrow is pointing in the direction of the fluorine, away from the hydrogen. And look what I did on the back side of the arrow. I made it into a little plus sign. The back side of the arrow kind of looks like a plus sign. And so they're marking which side is the slightly positive and which side is the slightly negative. We never do that. I'm just trying to expose you to some of the other ideas you're going to see when you get to like level 17 of chemistry. Get to 14th grade or whatever. Dipole moments, or dipole moments. When we draw the Lewis dot structure, we can often trick ourselves. But when we build it, we can't. It's a lot harder to trick yourself with a model in your hand. But first we'll start with HI. I thought I'd already drawn this, but I guess I hadn't. So we have hydrogen and iodine. And iodine has 7 valence electrons. And hydrogen has 1. And they're going to share those in common. So we have a bond between the hydrogen and the iodine. And we're going to talk about octets and all those exceptions in a little bit. But which element is stronger This one's real tricky to figure out. If you like look at phosphorus versus iodine, because we substitute H for P, you got that stupid diagonal, don't you? Iodine is just barely stronger than hydrogen. So you couldn't really predict which way it was going to go. You would need data for this question. All right? And then if they gave you the data, 2.3 and 2.2, you'd be like, oh, if iodine's 2.3 and hydrogen's it's actually 2.1. The iodine's just barely stronger. So the dipole moment would be going towards the iodine. Or you could put little slightly signs on there, the little lowercase deltas. Do I need to draw the nitrogen one to figure out if it's going to have a dipole moment? It's two identical elements, right? So it's nonpolar covalent. The third one, though, that's the one that messes people up, because they draw it like this. And this is a really deceptive way to draw it. And technically, I should have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I'm being very sloppy here, sorry, because that's not really the point of this question. The way it's drawn, it looks like the fluorines are opposites of each other, and the chlorines are opposites of each other, because this is 2D world. Do you remember what shape that is? It's tetrahedral. And in the three-dimensional world, the tetrahedrals, you have like two that are up and two that are down, or you can imagine it like that. So the chlorines aren't actually opposite of each other. They're both down. And the fluorines aren't actually opposite of each other. They're both up. And that's one of the reasons you have to build the models. Secondly, when you build the models, let's say that Penn State builds the models, okay? And Def Leppard is just watching. Don't do that. Pick up the model. Hold the model. When you hold the model in your hand, do you think you're using the same spot in your brain as when you look at the model? No. The second you touch something, you engage a new spot in your brain, and you're making connections and storing information in a completely different spot. And that's a valuable thing with complex models. Cool? So just because you didn't build it doesn't mean you shouldn't hold it. Because you do, you just kind of put it in a completely different zone. Also, with all of these model things, there are some great websites. And I'm not going to give you the whole long string, but if you Google this website that I am thinking of, I'm going to have to come back to it. I can't think of what it is. I'll get it later. Okay. So we actually did this last chapter. I wrote out the electron configurations for magnesium, phosphorus, boron, bromine, and rubidium. I don't know what that other word was. What type of charge does magnesium take? +2. Which electrons do you suppose it gives off when it takes the +2? Yep. Those are the 2 electrons it loses, and then it's got a noble gas configuration left, doesn't it? What type of charge does phosphorus usually take? Oh, I should say the right thing. What type of oxidation state does phosphorus usually take? -3, which means 3 more electrons. So this guy here is actually 6 if it's phosphorus -3. And then bromine, -1, because that's 1 electron away from being full. So this becomes a 6. And what about rubidium? +1. So it loses that last one. And you can see that bromine and rubidium actually have the same electron configuration as ions, because they are isoelectronic to the same element once they're ions. And that term is also right there, isoelectronic. Yes? Yep. There's just, yeah. We're just reinforcing that when they take an oxidation state, their common oxidation state, they're typically shifting to a noble gas configuration. It does get a little bit more complicated when you have a transition metal. We talked about with the transition metals, you would go for the valence electrons first and then dip into whatever was going on with the d orbitals. If I am magnesium and I lose 2 electrons, someone else must be picking them up. They can't just disappear. Well, they can, but that's a different class. So they can't just disappear. They must be going somewhere. And they have to be picked up by a different element. So at the bottom, we have magnesium with a +2 charge. Why do there have to be 2 chlorines? That's how you balance the okay. The electrostatic charge of magnesium is +2. The chlorine can only take 1 electron. Magnesium's giving off 2, but chlorine can only take 1. There has to be another chlorine to accept the second electron. And so the ratio of magnesium to chlorine is going to be 1 to 2 in any sort of solid that's created or any sort of ionic compound that's created. Ionic compounds are neutral, electronically neutral. We already hit ionic size last chapter also. As they gain electrons or lose electrons, do they get bigger or smaller when they lose electrons? They get smaller. They get smaller. If they gain electrons, they would get bigger. Yeah, they would get bigger. I'm sorry, it's too funny to record that stuff, so I had to pause it for a second there. He still looks funny. So as they gain or lose electrons, we see a shift in size. If they gain electrons, they're getting bigger. Also, you have to take into account, if you're comparing like these elements here, wait a second, make sure I'm on the right thing. These elements here are not isoelectronic. These 2 elements are on different periods, so there's going to be a shielding effect issue. And so tellurium being a period below selenium is definitely going to be a bigger atom than selenium. Okay. This is actually new. There's been a whole lot of review so far, hasn't there? Maybe re-explanation of some old ideas. But this is the first of the new things. We don't actually do this math. I don't want to be clear. All I did to get my answer here of -436 is I added together these 5 numbers. Right? I added 64, 419, half of the bond energy, which gave me 120, this and this. I added those 5 values together to get the 436. Not much of a math problem. But scientists wanted to try to understand when, what am I even making here? When potassium and chlorine bond together, why is this much energy being given off? What steps can we kind of represent them by? And so they did a bunch of tests and they realized there's 5 different things occurring when bonding happens. The first thing is that the atom that was potassium as a solid must be breaking free from the other potassium atoms. That's a state of matter change from solid to gas. So they calculated how much energy does it take to turn solid potassium into gaseous potassium. Boom. And they wrote that down. Okay? The second thing is that potassium has to be losing its electron because it's giving its electron from potassium to the chlorine. So they were like, well, how hard is it to take away the electron? That's the ionization energy, isn't it? Right. That was not my fault. He's okay. The bleeding will stop eventually. He broke the chair. The bolt fell off. He's good. He's good. Okay. Take the electron off. Now on the other side, I've got to break the chlorine in half. Yeah, you just move that chair aside. Blame it on somebody else. Yeah, the screws fall out every once in a while. For those of you playing at home, a chair just fell apart because a screw came out. There's 2 atoms are bonded together. Yes, we're holding hands now. And that bond has a certain energy in it. If you wanted to break this, you'd have to work hard because this is a handshake you can't break, right? And so you'd have to put some energy in. Oh, there we go. And that energy, I hit my hand. The energy breaks in half. Half of that energy goes to me, the other half to him. And so that's why they've divided that 1 value in half. Now there's the congratulations, you just got an electron. We call that electron affinity. When you receive an electron and energy is released. And then there's the final, the positive potassium and the negative chlorine come at each other and reach that energy position dependent on distance. And that's called the lattice energy. these 5 things are all happening simultaneously when potassium and chlorine interact. And so Def Leppard can, actually mix potassium and sodium together, measure the amount of energy given off using some thermodynamic stuff we're learning later in the year, and get a value. Whereas Penn State could do all 5 steps separately on paper and show that he should get the same thing. And so we were really happy when we finally explained mathematically what was happening at each stage. So another way to look at this is in terms of a diagram. See this nasty diagram you have here. The green part down at the bottom is the overall change. You see the amount of energy. Where does it start? It starts right here. The amount of energy to turn magnesium into a solid, a little bit of an increase. Then you have to take the electrons away from magnesium, a big increase because you take away 2 from magnesium. Then you have to break the bond from the 2 oxygens. Boom, now it's a single oxygen. And then the oxygen steals the electron. Boom. And then the magnesium and the oxygen get attracted to each other finally. Huge energy release. Huge energy release when they get bound together, because that would be a positive 2 times a negative 2 in that energy equation we were looking at earlier. And so it's a big energy release. So the amount put in versus the amount that comes out, which is greater? The amount that comes out. So when magnesium and oxygen react, it's exothermic. There's more energy given off than there is energy put in. Cool? You've burned magnesium and oxygen. It's bright white light. You have to look through plate glass to see it. You have to put energy in with the Bunsen burner. And then once it finally ignites, you get a lot of energy back, don't you? But you can't see these little steps along the way. Someone just kind of showed it mathematically to show that what occurs here is made up of a bunch of little steps. Cool? Ma'am. Yes, ma'am. No. What you're supposed to understand, though, is that if the energy put in is less than the energy out, then it's exothermic versus endothermic. Energy released versus energy absorbed, right? So that's really where I was going to go, is that these diagrams just represent all of the changes, and you sum them together, and you can figure out if it's exo or endothermic. This would be the same thing. We're actually going to skip this one. You would add those 5 values together, and you'd either get a positive value or a negative value. Okay? So. Negative means, so good question. If you get a negative value, more energy is released than absorbed. So relax, don't do it, boy. He puts in 50 joules from his propane into the magnesium, but then he gets 70 joules back. So it's actually a net of negative 20. There's more released from the, it's exothermic, right? If you have an exothermic reaction, from the reaction's perspective, and that's the perspective we're supposed to look at, it should be negative. It's losing energy. It's releasing it to you. Anytime you pick something up and it feels hot and it burns your hand, the something is losing energy. It's exothermic. You're gaining the energy, ouchie, right? And that's the hardest thing to understand, is it's not about you or even me, even though I feel like it should be. It's about the reaction, right? Did the reaction gain energy or lose energy as we made these new compounds and molecules? So ionic and covalent, nothing is ionic 100%. There's always this part where the ions approach each other and they kind of pseudo-share the electrons. The only time we have a true non-polar covalent is when we have identical twins. We have oxygen and oxygen, or fluorine and fluorine. In question 3, what do we call these things I'm circling? Polyatomic ions are held together through covalent properties. They're sharing electrons, but they also have a charge on them, don't they? So they also have ionic properties. So they definitely straddle the line of both sides of the covalent ionic. Oh, I just recorded a hiccup. That's awesome. The common accepted definition across all chemistry for an ionic compound or salt is it conducts electric current while melted. So if it's in the liquid phase, does it conduct electricity? Salt, sodium chloride, NaCl, will conduct electricity if it's a liquid. And I want to make it clear, I don't mean dissolved in water. That's different. That's aqueous, right? I mean, if you heat up your table salt to, I think it's 1,200 degrees Celsius, it is now a liquid salt. And it's a little too hot for your French fries. But as a liquid salt, you can conduct electricity through it. As a solid salt, you cannot. All right? Electricity won't flow through it. This should be a lab, right? At a place that's more secure and safe than this one. This is just a graph showing the relationship between ionic and covalent bonds. And why do you suppose all of these over here are considered ionic? Look at the elements in question in the graph. They're far apart. You've got metals and you've got non-metals. There's a huge difference in their electronegativity, so they're going to have ionic bonding. On this side, where did we say hydrogen really should be? So those are all pretty close together in terms of their electronegativity values, so they're pretty much considered covalent or polar covalent. I would like you to do something weird with this chunk of your notes. I want you to open your textbook when you get home and fill this section out. I want you to actually try and read a book. I know, that's a freaky thing. But I want you really to notice that your textbook has valuable information in it. And a lot of people aren't using it. Show of hands of who's using their textbook every night. Oh, there's a 1.5. That was more than I was expecting. I was expecting a resounding none. That makes me happy, just 1.5. I would be even happier if everyone had been like double hands. The textbook is not easy to read. It's a college textbook, right? So you've got to get used to reading those now because you're going to be paying $150 for them in a year or so. It's better to know how to read one now. I'm going to pause for a second. No. If you want to write in your textbook, buy one online, not a digital version. Go to Amazon, go to any of those websites and buy one for pennies on the dollar. The textbook you have that we gave you, $130 textbook. Buy it on Amazon, $15. You can write all over it, or even better, buy the last version. None of the words changed. The graphics got updated. You can buy an old textbook with all the same words for like $2. The shipping will be more than the book. And then you can write all in it. All right. Same goes for college textbooks. The only time you get really ruined by that is if the professor released a brand new one and he's just changed it. You know. The one thing I want to kind of hit on this though is number 8, the limitation of a model. Lewis dot structures are a model. Building the little 3-dimensional models are models. Are they right? Are they 100% perfect? No, they lack the elasticity, the fact that the electrons aren't sitting in place, that things kind of vibrate and move and have motion to them. There are some decent models in computer programs that work pretty well. And if you Google PhET, I knew it would come to me, P-H-E-T, and then do molecular models. If you do PhET and molecular models, you can do a lot of the, I want to have a molecular model for NH3. You can pick a nitrogen and 3 hydrogens, and it goes boom, and it's 3-dimensional, and you can rotate it around. You can quiz yourself with it. You can be like, I think that's trigonal pyramid, and then click it, and it'll tell you the right answer. And you can build, I think they've got like 45 different molecules you can buy. It's right there, PhET molecular models. If you just Google PhET and then molecular models, we've been using it for about 10 years. It's pretty decent. And it even does the other funky shapes we're going to talk about today. And you can build all sorts of stupid things that don't exist also. Yes, not yet. Yeah. You haven't gotten to it yet. So you actually have table 8.4 in your notes on the next page. It's a bunch of data. And some person, let's just call him Ethan, had to go through and break all of these, not that Ethan over there, because he's good at breaking stuff. Had to break all of these bonds apart. So he's got the bond. I'm holding hands with pink shirt. And they're pulling on each other. We're pulling on each other. It's strong. And then he had to keep, oh, no, that didn't do it. No, that didn't do it. No, oh, okay, that much energy. And then they measured it. That's the energy to break that bond, right? Then there's also the, hey, it's good to see you. There's also energy released when you shake hands. You ever feel good when you shake someone's hand? Like some people. I'm not saying everyone, you know. I see your faces when you shake mine. But when they shake hands, there's also an energy situation going on. Do you think those are the same? Is breaking the same as forming? No. It's a very opposite relationship. The formation is exothermic. Ta-da! Energy released. But to break this, you're going to have to work hard because this teacher-student bond is strong. You got to put a lot of energy in. You got to put a lot of energy in, and eventually it'll break. Ooh, that was a good sound effect. And so those values are all known values and just data. But if you wanted to figure out like how hard it is to break apart water's OHs, I have an OH value here. I would need to put in that many kilojoules to break apart that bond. But guess what? In a water molecule, that bond occurs twice because it's H2O. So I'd have to do that again to break the other bond. Cool? Or what if a hydrogen meets an oxygen? That much energy would be released. All right? So you actually have this typed right into your notes. It takes energy to break bonds. That's endothermic. The value for the bond energy is positive. If you are forming bonds, energy is released. From the elements reactions perspective, that is a negative value. It's the same numbers, just whether you put a plus sign or a minus sign in front. Okay? If bonds are being formed, it's negative. If bonds are being broken, it's positive. So let's pick a couple people. I got rainbow shirt gymnastics in the front. Is that a gymnastic shirt? A volleyball. Why don't you find hydrogen on the data table? Tie-dye shirt behind her. Why don't you find chlorine, okay, in purple sweater. Why don't you find hydrogen to chlorine on that data table right above, okay? You see the data table on your sheet right above? Right there, okay. What is hydrogen to hydrogen on your data table, Hannah? 432. So I'm going to try to write down 432. Now I got a question for everyone else in the room. Are we making or breaking hydrogen in this reaction? Are we making hydrogen? No, we're making hydrochloric acid. We're destroying hydrogen. We are breaking the bonds between the two hydrogens. This value that she just gave us is a positive value. Okay? Now, tie-dye, what about chlorine? Is that a positive or negative value also? Are we making chlorine or breaking it? Breaking it. So it's a positive value. We're going to, if these two chlorines are bound together, we have to put energy in until they break apart. Now we are making hydrochloric acid. What's the hydrochloric acid value? 427. But wait a minute. We're making two hydrochloric acids, aren't we? So that bond isn't occurring once, 427. It's occurring twice. So I'm going to take that value and multiply it by 2. What else do I need to do to the 427? It has to be a negative value because that is the energy that would be released when the H and the Cl bond to each other. Now I add those three values together and I have the energy of this reaction. Okay? If I add, how much does it take to break the hydrogen? How much does it take to break the chlorine? How much is released when I make the hydrochloric acids? Cool? That data table is also found in your textbook in case you need it. It is also found on the internet in about 1 billion different places. So we should get negative 183 when we do that amazing math. These are the same values you gave me, right? You said 432 and 239 and 427. I usually do reactants minus products. Why do I do reactants minus products? Yes, because the products are being made, so all the product values are negative. And then I just put the reactants in parentheses and add them up. And then I subtract all of the products at once. It would work if you had multiple products. So in this reaction down here, I'd have the reactants minus the products, and then I would get the energy for that entire reaction. Okay? Would I have to do anything to the values I pull off the table for that reaction? Heck to the yeah. I have to multiply the fluorine by 4 and the HF by 4, don't I? Right. Ionic structures of solids. This is something that's actually really easy. Again, they're attracted to each other by their charges. We already hit this. If you try to push the ions closer together or pull them farther apart, it doesn't work so well. There's a best distance. Why do you suppose when the two ions get close together, it's not the best distance? What would happen if you got two ions way too close together? The other energy levels would start to overlap, wouldn't they? And they would repel each other off. And if you get them too far apart, then the attraction's being really, really diminished. So there's a best distance. And as the positive and the negative approach each other, that best value would be the maximum energy release. So we don't calculate that. We can just look at a graph and say, okay, yeah, that right there is the best spot. It's the most energy released. All other positions aren't as good. When a solid crystal's formed, that occurs a billion times. I'm a chlorine, you're a sodium, he's a chlorine, she's a sodium, he's a sodium, and it goes back and forth, and that math problem is occurring again and again and again and again. And with every single solid that's out there, these values are balanced off of each other. This is titanium oxide, and the distance between the oxygens and the titaniums are maximized for the energy release. Most of y'all didn't do earth science, is that true? No one? You did earth science? You did? And so they get into earth science, a little bit of the different shapes of crystals and how they build together. That's really super duper intense chemistry. They don't do the chemistry, but just the fact that like how the atoms are arranged is actually intense chemistry. We're going to get a little bit more intense with that next unit, but not this unit. Just the fact that the positive and negatives are trying to minimize the energy interactions. So, metallic bonding, if you have all iron atoms, you have a sea of electrons. That's the common phrase, because all of the iron atoms are pretty weak. Their valence electrons are just kind of floating around in there. And if he takes my valence electron, I might take hers, and then you take his, and they all just float around. And the valence electrons are often swapped and shared because no one has a good grasp on their valence electrons because they're weak electronegativity-wise, and they have a lot of shielding, which means that metals can easily conduct electricity because their electrons are a little bit loose. It also makes them strong as solids because if you take mine, there's plenty of other electrons available for me to kind of borrow, and they can shift their electrons around. Here's a good one though. This is an interesting question that was asked a couple years ago. Why does sodium have a melting point of 98 while magnesium is 650? Look where they are. Can you take a guess as to why magnesium's melting point is so much higher than sodium's? That is a big part. And then we were also just talking about valence electrons. How many valence electrons does magnesium have? 2. And so there's more valence electrons floating around in the sea. And so there's a lot more swapping, and it's harder to really break these atoms apart because, oh, you took my electron? I'm going to borrow one from him. And they just all shift around constantly. You could probably predict that aluminum would be even higher, couldn't you? because it has more valence electrons and a higher effective nuclear charge. So, we literally just went through that. We're going to go down to the next thing. The two types of alloys, I'm going to just skip right to the picture because they're much easier to understand. A substitutional alloy. This is me, the common metal, and Shangri-La, just about the same size, right? A little grayer, not as red. Oops, I recorded that. Are they about the same size? Do copper and zinc appear nearby on the periodic table? They'd have very similar properties, and so they interact with each other pretty well. And that's the alloy we call brass. The alloy we call bronze has tin in it. Tin is another energy level lower, slightly bigger atom, so it's not as strong because that atom wouldn't just fit right into the hole. It would cause weird spots in it. Yeah. Tin? If you have TIN, yeah, I know I supposed to say tan when I supposed to say tin. Just struggle with that over pronunciation. Interstitial is where smaller atoms fit inside the tiny holes in between them. And you see the carbon atoms are kind of occasionally filling a gap between those iron atoms. That's what we do with steel. I think steel was actually first accidentally made, where someone accidentally got some ashes inside the mixture of iron that they just melted down, and then the sword was way stronger, and they won the battle, and they were like, let's put the ashes in there from now on. Ashes, when you burn charcoal, have a lot of carbon in them, and you put too much carbon, though, then it's filling all of the holes, and it becomes really brittle. So an interstitial alloy is when an atom is kind of filling in those little gaps. Cool? Localized electron metal lone pairs. We're getting into Lewis diagrams finally. Whew. So when we talk about drawing Lewis dot structures like this nitrogen trifluoride, I have some electrons are stuck in between the elements. You might say that they're in a certain location. They're the localized or stuck in location electrons. This model is the one you know. You actually already know the localized electron model. You've drawn Lewis dot structures. It's the idea that electrons occupy locations. There is a completely different model that is horrible, unless you're that guy, called the molecular orbital model theory, where you take the SPDF stuff and you imagine it at the next level. When they bond, what happens to the s orbital? What happens to the p orbital? How do they merge together? What's the energy changes? We don't get into the energy changes, but we will look about how they shift a little bit. It's not too terrible. We usually only care about the central atom. I'm going to circle the lone pairs in green, right? And then I'm going to circle the bonding pairs in purple. And I don't really care about the fluorine's extra electrons. They'd have to be there so I get my octet. What did octet mean? Trying to get to 8. The first thing I did in my head is I counted across to nitrogen. I said nitrogen is 1, 2, 3, 4, 5 elements over. It's got 5 valence electrons. It's S2P3. And so if it has S2P3, how many more electrons does it need to get to the octet? 3. That's simple math. I have 5. I need 3 more. Tells you how many bonds. Right? Fluorine has 7. How many bonds does it need? 1. So I made a single bond to the nitrogen, boom, 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 and knocked out the nitrogen and the fluorine at once. I went ahead and drew all these because I knew I wouldn't be able to draw them live with any sort of skill. I know who I am. Yes.
So when they bond, is that each atom trying to get a bond there?
Yes, unless they're one of the exceptions. We're going to go through the exceptions list. The exceptions list is unfortunately larger than it used to be. But if you're dealing with your basic elements, nitrogen, oxygen, phosphorus, sulfur, so nitrogen, oxygen, fluorine, chlorine, you got 7, you're trying to get to 8. If you can't get to 8, then just pretty much assume it's an exception and work your way there. We'll hit the exceptions in just a second, though. I like to color code my work so that I can tell who's who. In number 11, I did the initial valence electrons. B was a -3 charge, so I added 3 in purple, just so I could tell. Right? Barium's usually only has 2. Here's barium plus 2. They're gone. Right? So anytime there's a charge, you're supposed to put them in brackets, and then you're supposed to show the charge outside the brackets somewhere. Oops, I forgot to do it on that one. There we go. And then down here on 12, I wish I had color-coded them different, but I color-coded the ones that are being shared for emphasis. All right? But no, I didn't. Yes, I did. I color-coded the ones that were being shared. The ones, ooh, that's a double bond. Look at how many are being shared between the carbon and the oxygen. That's exciting. And then these are 3 single bonds, unshared pair. Does that look familiar to y'all? All right, cool. Exceptions to the octet. Wouldn't be chemistry without a lot of exceptions. All right, I got about 10 minutes or so. There are a bunch of exceptions because, well, last year you had hydrogen. Hydrogen was happy with 2. Let's just make a short list here. Hydrogen was happy when it got to 2. And then you had beryllium. Beryllium was happy if it got to 4. Oh. And boron. Boron was happy if it got to 6. I don't know if you ever noticed this, but those 3 elements are the first 3 at the top: hydrogen, beryllium, and boron. See H, B, E, and B, kind of like across the top of the periodic table. And I just always remember 2, 4, 6. They have to be in pairs, and 2, 4, 6 as I went across. That's the way I kind of jogged it in. After 6 comes the number 8, which most elements are hunting for 8. And that's your octet. And then we also talked about phosphorus and sulfur last year. And we said that phosphorus and sulfur could be 8, 10, or 12. Well, why can phosphorus and sulfur be 8, 10, or 12? They are on the 4th energy level. Sorry, they're on the 3rd energy level. And on the 3rd energy level, isn't there a d orbital? Do phosphorus and sulfur have any d orbital electrons? No. So that space is empty. There's no electrons in that space. It's got 3s and 3p electrons, nothing in the 3d, which means if bonding occurs and there's empty space, can electrons get pulled into that empty space? That's why phosphorus and sulfur could violate the rules. Well, guess what? There's a lot of empty d orbitals as you move in that little area. If you go down to arsenic, right below phosphorus, arsenic, yeah, moron. Arsenic, right below phosphorus, arsenic's 4p something. Does arsenic have any 4d electrons? So it can use the empty 4d space to create funky exotic shapes. What I'm trying to say is anything that's below phosphorus, anything, if you make like a corner, this little corner where phosphorus and sulfur are the top left of the corner, all of those elements are cheaters. All of those elements, including the noble gases. What? Yeah. We're going to do some xenon molecules and some krypton molecules, but xenon and krypton, being noble gases, are incredibly difficult to form molecules. So there's only one element that typically can do that. It's the biggest punk on the periodic table. It's fluorine. Why do you suppose fluorine can do that to xenon, but other elements can't? It's got the highest electronegativity. It's walking up to the noble gases and say, "Oh, you think you're noble, huh?" and it's messing with the electrons. So even though the noble gas already has 8, its d orbitals are empty on that energy level, and the fluorine is moving things around with its extra strong electronegativity. Look at these amazing drawings. Again, I knew I wouldn't be able to draw live in front of you. So iodine usually has 7. I did them in red. Fluorine usually has 7. I did them in red. What's the green? one extra electron. All right. If iodine has 7, how many bonds does it need to make? 1 or more, because it can have more than 8 electrons. It's in that zone. My advice to everyone is draw the dots down. Go for 8. If you can't make it with 8, try 10. If you can't make it with 10, try 12. If you can't make it with 12, erase everything and start over. You have done messed up. Watch out for occasional double bonds. This is going to be just experience and a little bit of practice. You might be looking at this weird iodine one and going, it's got a bond, a pair of electrons, and another pair of electrons. That's electrons in 5 different directions. I don't know that shape because you don't know that shape, all right? All of these, we have a really stupid one here with this nitrate. I hate drawing nitrate. I have to pause because you can't draw nitrate a simple way. One of the electrons on nitrogen is actually being moved to one of the oxygens. There's no simple way to draw nitrate. It's one of my least favorite ones. Unfortunately, it's very common, isn't it? So nitrogen usually has 5 valence electrons, 1, 2, 3, 4, meaning these 2 are still on nitrogen, and I kicked one out to the oxygen there. Those drawings are hideous, so I also have them line structure-wise. Is that better? This is the same 6 drawings, just with lines instead. Look what I did with that funky oxygen. That's not a bond, that's an arrow, isn't it? That is not a required skill in AP chemistry, but what that arrow tells me is that nitrogen gave an electron to the oxygen. That's one way people indicate that stuff. In your textbook, that's called a coordinate covalent bond. Like the electron had to be handed off and then bonded, and that takes more coordination. The electrons had to be moved around. Resonance structure is the idea that there's multiple correct answers. Several times there will be multiple correct answers. Some answers are slightly better than others. If you're asked to just draw a Lewis dot structure, any one of the right answers is considered right. But in all of these drawings, the shapes are the same. This has the same total number of electrons, 1 pair, 2 pair, 3 pair, 4 pair, 5 pair, 6 pair, 7 pair, 8 pair of electrons. 1, 2, 3, 4, 5, 6, 7, 8 pairs of electrons. I didn't change the number of electrons, I just moved where they were. Guess which one's a better drawing? Well, they're both fine, but one of them is more stable. Yeah, this one's a more stable form. This one's less stable. And the reason it's less stable is because the oxygen on the right starts off with 5 electrons and then makes a triple bond. The oxygen on the left starts off with 7 electrons and makes a single bond. That's not terribly stable. And then in 15, that also works. There's a -1 charge, which I made red. You can do it 2 different ways. My least of all is this scenario here. Odd electrons. Neither one of these drawings work. And that's the right answer. Neither one of them work. Because the right answer is that they shift back and forth. It shifts back and forth which one has the correct number of electrons. I don't ever see those questions. They just are a thing that does exist. If this existed and you breathed it in, do you think it would last long in your body? No, it's an unstable molecule that doesn't have its octet satisfied, so it would react really quickly. So those don't exist very well in the natural world. Yes, BB.
So, if a molecule has resonance structure, does it change, stay at one, or does it move?
Well, so one of the things we're talking about models being static versus in reality they shift. This is carbon dioxide. This is the most reasonable model. But if one of the electrons gets excited, it could shift and become one of the other versions of it. And that's one of the reasons carbon dioxide can absorb energy more than some other molecules, is it can shift its electrons around as it gets hit. And some of that excited energy can be converted into kinetic energy also. Which model's better? This one. And the way you figure out if it's better is you kind of cut these ions. You cut these in half, and you look at the two halves, how many electrons after I cut this in half does this sulfur have? Bond, you only cut it half the bond, right? So 7. So the sulfur has a -1 charge, where on the other side, the nitrogen has 1, 2, 3, 4, 5. It's got its normal amount, doesn't it? And the carbon in the middle has 1, 2, 3, 4, its normal amount. So the sulfur is the only thing with a charge in there. We call that the formal charge. When you cut the molecule up, that's actually the next thing in the notes. When you cut the molecule up and say, hey, who has most of the electrons or who doesn't? It's called a formal charge. And I have an example of this right here, POCl3. So I went ahead and I cut the molecule apart. The bond between the phosphorus and the chlorine is cut in half. Chlorine has 7. That's its normal amount. It doesn't have a charge, does it? This chlorine has 7. That's its normal amount. It doesn't have a charge. This oxygen has 1, 2, 3, 4, 5, 6, 7. That's not its normal amount. That oxygen has an extra electron. So the oxygen's formal charge is -1 in this formula. What does phosphorus usually have on the periodic table? How many valence electrons does it usually have? Usually has 5. This phosphorus here, 1, 2, 3, 4, it's lost an electron. So this phosphorus has a formal charge of +1. It's lost one of its 5 valence electrons. So a formal charge is just a way of looking at who has more ownership of which electrons, and it helps us figure out oxidation states as we move forward in the year and we do redox reactions. But that's not something I'm going to bring up right now because it's scary. Okay, we need to practice drawing. I ran out of time in my drawing, but I really want to get to this. These are the shapes you know up here. Linear. You know, remember the linear? Those were good days, weren't they? Trigonal planar versus tetrahedral. I'm going to circle the 5 you know. These are the 5 you probably remember from chemistry. Bent, trigonal pyramid, tetrahedral, trigonal planar, and linear. Do you want to start with linear? 2 directions. Are there any other electrons on it? No. So a lot of kids will label things like, that's 2 directions with 0 extra electrons. OX 0 extra. How many directions is this going in? 3 directions. Does it have any extra electrons? 0 extra. Right beside it, this one has bonds in 2 directions and an extra pair of electrons, doesn't it? See a little pair of electrons on top? That's a new one. 2 directions, 1 extra pair. What's 2 plus 1? 3. These both have electrons in 3 directions. Some of them are bonded, some are unbonded. Tetrahedral has bonds in how many directions? 4. Trigonal pyramid was 3 directions and an extra pair. And your good old bent was 2 directions and 2 extra pair, wasn't it? 0 extra on tetrahedral. So this one is 4 and 0. I'm just going to write them down as 4 and 0, and then 3 and 1, and then 2 and 2. Okay? Then we get down here to the fun ones. All of these have electrons in how many directions total? 5. And all of these have them in 6. Let's point out some funky names. Linear. What the hell? Linear, a frickin' again. And when you do those linears, keep in mind the bonds are going to maximize the distance apart. So they go for the maximum distance, and then those 2 linears, there's only 2 bonds and a whole lot of extra electrons. All right, I'm done.